Section 5.5 in your book covers the substitution rule, also known as u-du substitution or u-substitution. Chapter 5.5 in Stewart's Calculus with Early Transcendentals, 7th edition. So what do you do if you've got to evaluate an integral like this one right here? It's nothing that you can change with algebra. Regular indefinite integration doesn't work. So what can we do? If you notice in this integral, a little function, 1 plus x squared, is being acted on by a big function, square root x, and it's got another function outside. So what we're going to do is think about what we can do to change this integral. Again, the two things you always think about first are, will traditional indefinite integration work? And can we use algebra to simplify? Because using your algebra skills is always easier than using u-substitution. So you want to be careful not to do an unnecessary u-substitution. Let's see how we do this. Remember that we can add something to the problem. We can rename things. The first time you renamed something was in probably pre-algebra or even before that when you used a let statement to define a variable. Same thing we're doing here. We're going to, in this function, let u equal 1 plus x squared. Now we can do that, and we choose to do that, and you'll get better at recognizing this, but the little function being acted on by another function is the one that you want to pick to be your u. Once we get that u, the goal is going to be to replace or rename everything in this integral with a function or derivative of u. So let's find the derivative of u. We call that du dx equals 2x. We just differentiated 1 plus x squared, we got 2x. I'm going to change the way this looks. Du equals 2x dx. We're going to do that every time. So if you want to just go straight to du equals 2x dx, that would also be fine. Now if you notice in your problem there, highlighted in orange, you see 2x dx. See how I can replace that with this du in the function? And then u replaces the stuff underneath the radical. So let's write that. Our new integral looks like the square root of u du. Again, I replaced 2x dx with du. I replaced what was under the radical with just u because I defined that. You did that at the beginning. You picked out your u. You'll get better and better at picking those out as we go along. At this point, it might be easier for you to write this as u to the 1/2 du. The integral of u to the 1/2 du is 2/3 u to the 3/2 power plus c. The final step in u-substitution for indefinite integrals is to plug the x expression back into the function. So your true answer is 2/3 times 1 plus x squared to the 3/2 power plus c. Still important to remember the plus c. Let's try another one. In this function, notice highlighted in green, 1 minus 4x squared is being acted on by the square root. Since we see the x squared in there, you kind of know that your du is going to have an x in it. So hopefully everything will be taken care of. U, try to write a little smaller. U equals 1 minus 4x squared, so du equals negative 8x dx. Now this doesn't look quite like what we need to replace. Look, highlighted in orange, x dx is what we need to replace with some expression with du in it. The u takes care of this guy underneath to the negative 1/2 power, if you want to think of it that way, the square root in the denominator. So let's think, what can we do? Divide both sides by negative 8, and you can say that negative 1/8 du equals x dx. Now let's plug those in. Notice in this problem how we replace the x dx with the negative 1/8 du, but since negative 1/8 is a constant coefficient, it can chill out in the front of the integral. So now let's integrate. Negative 1/8 times 2u to the 1/2 power plus c. The final step is to plug back in your x expression. I'm going to have to move down here. And you get negative 1/4, because 2 times negative 1/8 is negative 1/4, times the square root of 1 minus 4x squared plus c. And that's your answer. Let's try this next one. The u in this problem is going to be 5x. See how the 5x is a little function inside of the big function e to the x? U equals 5x. Looks like we're going to have another constant coefficient. Du then equals 5 dx. So it looks like I have just a dx to replace, so I'm going to divide by the 5. 1/5 du equals dx. You want some expression of u to equal what you need to replace. Now I've got everything ready. E to the u du. I'm going to put the constant coefficient 1/5 out in the front because 1/5 du is what replaced dx. This equals 1/5 e to the u plus c. And plug in your x expression again. 1/5 e to the 5x plus c is your final answer. Pause and go through these again if you feel like you need to. You might be asking yourself, can you use this for definite integrals? Sure you can, if you're very, very careful. Let's look at this example. Obviously, the u in this example is going to be what's underneath the radical, the 2x plus 1. U equals 2x plus 1. Then du is an easy one, 2 dx. And all we've got to replace is a dx, so let's say 1/2 du equals dx. Now what we need to do is change the limits. That's the only extra step that comes when you have definite integration with u-substitution. Change the limits of integration. If you change the limits of integration, you don't have to plug the x expression back in at the very end, which makes it nice and easy because usually the u expression is a little bit simpler. So let's think. When x equals 0, u equals 2 times 0 plus 1, or 1. When x equals 4, u equals 2 times 4 plus 1, or 9. So let's write with our new limits of integration our expression with u. We replace the dx with a 1/2 du, so I need a 1/2 out here in the front. My integral is now from 1 to 9, watch your order there, times u to the 1/2 power du. When I integrate this, this should be your answer. If you don't have this answer, pause and go back. Try to redo the definite integration. Now, take a couple of minutes and try these 5 problems. Pause the video now so that you don't see the answers. Here are the answers to these problems. The one that I want to highlight, all of them are pretty straightforward except for number 5. Pay attention on number 5. We had to do a little more substitution than usual. We let u equal 1 plus square root x, which is what we've been doing all along. And then du is 1/2 x to the negative 1/2 dx, or 1 over 2 root x dx. This is where it gets tricky. We need to multiply the 2 root x because in our original up here, there's nothing to replace with a 2 root x. So I need to multiply that to the other side. 2 root x du equals dx. Then, it's a square of thought. It should be like a thought bubble, but here's what I was thinking. I thought to myself, if u equals 1 plus root x, then root x equals u minus 1. So here's a place to put a u minus 1 instead of the root x. Now I got everything in terms of u, and I can plug it into my function. Remembering to change the limits of integration by plugging them into our original u up here. So I've got 2 times the integral from 1 to 2 of u to the negative 4 times u minus 1 du. This the 2 u minus 1 du replaced the dx in the original problem. And this one was to the negative 4th power. So then just evaluate that like you would any definite integral. Your answer should be 1/6. Go back and try that one again if you feel like you need to. We'll practice more of these in class tomorrow. The final things from this section that are important are these symmetry rules. They're pretty easy, and they come up randomly in odd problems, and you just need to recognize them. But the important thing you need to know before class is the difference between an even function and an odd function. An even function has symmetry about the y-axis, or f of negative x equals f of x, and an odd function has symmetry about the origin, or f of negative x equals negative f of x. And if a function is even, then the integral from negative a to a is just 2 times the integral from 0 to a. If you think of an even function like pretend that's y equals, or f of x equals x squared. Remember, the integral finds the area under the curve, so if this is from negative a to a, see how it's twice the area? So you could just find the integral from 0 to a, which is sometimes easier, and double it. Let's try to draw one that's symmetric about the origin. In this one, you can see that if this is your negative a, and here's a, that this negative area over here is going to cancel out this positive area over here. The negative area down here cancels out the positive area here, and your answer would be 0. There's some quick examples there. That's just something to know.